we are using this random noise, and we want to predict instead of a random noise and something into which is called a real digits, just like this raw MNIST. Here is our final generated MNIST digits, which are generated using overtrained. That's how the final epoch's output looks like. First of all, let's understand what are the GANs. These are the Generative Adversarial Network, and it is a direct competition between the generator and the discriminator. After importing the libraries from Torch and Torch Vision and converting the device from CUDA, because we are training this on GPU, and these are the parameters we are going to use for our learning rates. Now we are going to create our class, which is a generator class, and tell Python it PyTorch module by inheriting from NN dot module. And think of this as creating the blueprint for our machine. The init function is where we build and name all the specific tools our artist will be using. Here you can notice one important point, that we are also passing the latent dimensions. This is the size of the random noise vector, the seed of the creativity. It is just a line of numbers, pure chaos that the generator has to learn to interpret as an image. So this is the latent dimension which is passed to this generator, and the generator will output an image out of this latent dimension, and generator needs to learn to create image from this latent dimension. That's the whole point of this generator as an artist, to produce AI generated images. So after that, the first major step is self.fc layer, and this is a fully connected layer. It takes over simple noise vector, which is a latent dimension, and dramatically scale it up to a huge number, which is 256 multiplied by 7 multiplied by 7. We are taking that tiny line of clay and turning it into a massive organized pile of features. And after that, we created a batch normalization 1D and nn.relu to learn the non-linear functions. These are the helpers. Batch normalization stabilize the learning, and the relu is a non-linear function that introduce complexity, making sure that the relationship between the input and the output is not just a straight line. So this part projects the noise into high dimensional space ready to be shaped. So that's the basic building block created from this latent dimension. Next, we move to the deep convolution layers, and rest of the step and the work happens in here. So this is the deep convolution core that builds the final image. First of all, it uses the transpose 2D. These are the key. Here you can see we are using it everywhere, and we pass them through a batch normalization and relu. And other than that, these layers are simply, our first layer is convolutional transpose 2D layer, and second is that layer as well, and after that we have simple convolution 2D layers. So these are simple convolution layers, and instead of shrinking image like normal convolution layer, this convolution transpose 2D do is these grew it. Instead of shrinking it, this layer grew it. So they take over small 7 by 7 map, upscale it to 14 by 14, and then again to 28 by 28. So they are responsible for adding details and increasing the resolution. The following convolution 2D layers maintain the 28 by 28 size, but refine the features like an artist adding subtle brush strokes. We slowly decrease the number of channels from 128 back to the 64, and we consolidate the image information. We keep using batch normalization and relu after most layers, and stabilizing and introduce the complexity. It has one output channel because we are probably generating a grayscale image like 28 by 28 MNIST digit. The final activation function is 10h, and this squeezes the output pixel value to be between -1 and 1. That is a common choice for GANs. because it makes the output symmetrical, which helps stabilizing the training. The core responsibility of this discriminator is to identify either the image being passed to this discriminator is a real or fake image. Inside that we have convolution 2D layers, and unlike the generator which grows image, the discriminator use standard convolution to shrink and analyze them. Notice the stride by 2, and in the first few layers that typically halves the image size, pulling out the more complex features at each step from 28 by 28 down to 14 by 14, then 7 to 7, and eventually down to a tiny 2 by 2 feature map. And the leaky ReLU, we use this leaky ReLU function everywhere instead of standard ReLU. We use this activation function which because it allows a tiny negative slope, which is crucial in GANs because it helps prevent the network from completely dying during the training, especially when features are strongly negative. The batch normalization 2D and dropout 2D layers, these we use batch normalization to keep the learning stable, and dropout layer is added as a regularization technique to prevent the network from overfitting to specific fake images and making it better, more generalized and critic. So the verdict self.fc, this layer, and once the image has been aggressively analyzed and shrunk into that dense 512 by 2 by 2 feature map, it's time for the final judgment via the self.fc block. First of all, it flattens it. This take out a 512 by 2 by 2 feature block and stretch it back into a single long vector of numbers. And the sigmoid activation function, the output of that single node is passed through a sigmoid function, which squares the value into a probability between 0 and 1. The value close to 1 means the discriminator believes the image is real, and the value close to 0 means it believes the image is fake. This single number is binary answer over detective provides as an discriminator. In the data flow in the forward pass is simple. The forward function shows the simple flow. The input image X goes straight into the complex feature extraction layer, which is self.main, and the result of that analysis is then classified by a fully connected layer, which is self.fc layer. In our case, a clean streamlined process from image input to a probability output is returned. And this function is designed to apply every layer in our neural network. It inspects each layer, identifies their types, and then sets its starting weight and biases according to a specific rules. Why bother using this? Because GANs, PyTorch default random initialization, often lead to training instability, causing the network to fight poorly. So what we do, if the layer names is convolution 2D, we come in here, and if we are seeing a convolution layer, means convolution 2D or convolution transpose 2D layer, we initialize its weight using normal distribution, just like this, a normal distribution. The crucial setting here are the mean of 0.0 and the standard deviation is 0.02. This ensures the weights start very close to 0 but are not 0, giving our convolution filter a tiny focus starting point, a common best practice for deep convolution GANs or DCGANs. So that's what we're creating here today. And next we handle the batch normalization layers. If our layer being passed is batch normalized layer, what we do, we have two learnable parameters here: the weight, which scales the data, and the bias, which shifts the data. We set the weight to start from around 1.0 with that small standard deviation of 0.02, and the starting the scale factor at 1.0 is intuitive, as it means the layer initially does not change the scale of the feature much. We set the bias, the shifting factor, to start at a flat 0, and by customizing these starting points, we give our GAN the best possible chances to converge and start generating awesome results right away. After that, we are just loading over MNIST dataset, just like we did in our previous tutorial. There is not much thing to explain here. Then we instantiate our generator and discriminator, and we apply our weights through weight initialization function, and then we created separate loss and optimization functions. Now that our models are built, they need a way to measure how well they are doing. That job belongs to a loss function. So we are using BCE loss, which stands for binary cross entropy. This binary cross entropy loss is perfect because our discriminator is performing a binary classification. It's trying to label every image as either 1, which means either it is real, or 0, which means it is fake. The BCE loss tell us exactly how wrong the discriminator's probability score is. Then comes the optimizer part. We bring the optimizers. These are the chaos that tell each model how to adjust its way to get better, since generator and discriminator have opposite goals. They need separate chaos. So what we do, we choose the Adam optimizer, a popular choice for its efficiency. We pass in the parameter of discriminator as netd.parameters, just like this, and we pass the learning rate just like this to its optimizer, and the generator parameter to its optimizer. Notice they also get their own learning rates, which means LRD and LRG. They both have their own learning rates, which controls how big a step to the model takes in the right direction. Tuning these can be key to successful GANs. So these are the key points to make a successful GANs. Finally, we have a small but incredibly important variable. We create a batch of 64 random noise vectors and save it. We call this fixed noise. During training, we feed this exact same noise into the generator every few epochs. Why? Because it allows us to track the generator's progress over time. If the generator is getting better, the images produced from this same fixed noise will consistently improve. It's our visual metric for success. Now come the important part, which is actually training the GANs. The code block that defines the core function of our GAN is the training loop. We start the process by taking over losses in G losses and D losses as an empty array first. The outer loop iterate through the number of epochs we need to train on. That's how many times we see the entire data set. The inner loop goes through our train loader, grabbing batch of real images one at a time. So it processes one batch at a time. The secret sauce: before training, we use a crucial trick for GAN stability, which is soft and noisy labels. And we do that by real and fake labels creation process. Instead of telling discriminator that real images are exactly 1.0, we use soft labels like 0.9, and we add a small bit of random noise. This prevents the discriminator from becoming too confident too fast. It keeps the learning dynamic and stops the generator from collapsing. It makes the critic job just a little bit harder. And the discriminator train first in two steps: real then fake. The real image, we zero over its gradient and add a little bit of a noise directly to the real image, which is another trick to prevent overfitting, and pass them to netd. We calculate D loss real by comparing the output to our soft real labels. Then comes the part of fake images. We generate new fake images from random noise using netg, which is a generator, and crucially we use .detach method here like this. when feed them into discriminator. This prevents the gradients from flowing back into the generator during the discriminator's update, ensuring they train independently, because we need to train independent discriminator and generator. Then comes the optimization part. We sum up the real and fake losses to get the loss, backpropagate the total loss, and update only the discriminator's weight using optimizer d.step. Now it's the generator's time to shine. Here comes the loop for generators too. The goal switch is the generator wants the discriminator to be fooled. So the generator is rewarded if the discriminator incorrectly classify the fake image as real. Then comes the double training part, and you can notice that this loop, we train the generator twice for every one discriminator update. Finally, we log our G losses and D losses. We save these losses and we print the statistic here. In this block, what we do, it temporarily disable gradient tracking with the torch.noGrad, use over fixed noise to generate a grid of sample images and plot the loss curve. This is how we visually confirm that. So here you can see the outputs. We create another plot where we plot both losses, G loss and D losses. With torch.save function, we save each model generator and discriminator independently into its own independent PTH files.